Hello, thank you for joining the Texas Instruments New Product Update webinar. Just a reminder that this is a weekly series every Thursday at 10 a.m. Central. A few quick announcements before we get started. This webinar will be recorded and available online at ti.com/npu. All phone lines will be muted, so if you have questions, please use the chat box and we will try to answer in real time, or you can contact your TI salesperson or field application engineer. Today's topic is how to use OPA X310 to drive high output current in low voltage applications. I will now pass it over to Robert Clifton for introductions.
All right, so good morning, everyone. Today we'll talk about how OPA 310 can solve two of your common application problems, which is improving drive strength or lowering power consumption. This is Bhuvanesh, product designer for this device, and I have with me Robert here, who's the applications engineer. We both belong to general purpose amplifier product group within TI. This is the agenda for today. We'll start with the device introduction. Then we have a few slides covering the product highlights along with the application scenarios. Finally, we will cover how to get started with OPA 310. So what is OPA 310? It is a 1.5 volt to 5.5 volt rail-to-rail input and output voltage feedback CMOS amplifier. It has got a quiescent current of 165 microamps typical. Also, it has got a very good offset over temperature of max 1.4 millivolt and a good thermal noise floor of 30 nanovolt per root hertz. It has also got a good gain bandwidth of 3 megahertz, and more importantly, it has got these three unique features, which is high output current, fast enable, and a fail-safe input ESD structure. Robert will cover the high output current applications, and myself, I'll cover the fast enable and the fail-safe input structure. Next, I'll be passing it over to Robert to cover the high output current application first.
All right, hello everyone. I'm Robert Clifton, and as Bhuvanesh mentioned, let's talk about the improved drive strength of the OPA 2310 from an application perspective. So let's start off with the LED laser driver applications. Many amplifiers require external transistors to properly drive the LED, mostly because of two different characteristics. First, the limited output currents at lower supply voltages, and second, this is the one that most people forget about, is the limited output voltage swing when directly driving the LED. So in this example, we have the OPA 374 that has an output voltage swing that's heavily limited, even at a typical LED current of 10 milliamps, and thus it requires an additional external transistor. So on the left-hand side, you can see that the OPA 374 has as an external transistor versus the OPA 310, which is directly driving the LED. And this is a result of its output voltage swing versus output current. You can see in the graph to the far right that looking at the 310, it has no issue. It's got a great output voltage swing even at these higher current levels. But the OPA 2374, you can see a severe voltage drop as the device gets past 10 milliamps. And even at 10 milliamps, you only see it's around 3 volts. So while the 3 volts might, while this unit that I tested here might be able to directly drive an LED, and emphasis on might, because the voltage drop of those LED diodes can vary depending on which one you're using. The real problem is this doesn't take into account temperature variations as well as process variations. And I'll go over that in a few slides from now, but you're going to want to make sure you have enough tolerance, enough headroom to be able to properly account for these kind of parameters when designing the circuit. And so I wouldn't recommend using a direct drive circuit for the OPA 310 like the OPA 310 has for the OPA 374. All right, thank you. So for the Howland current pump, this is a pretty fancy way of saying this is building a current source using an op-amp. And obviously for higher output current amplifiers, it's going to help reduce the need for more channel counts when you're trying to drive some of these higher current requirements. So this example, we have a 50 ohm load and we want to have 75 milliamps of current going through it. Most amplifiers, you're going to require 2 channels or even more. In this case, we chose a TOV 2772, which can output comfortably 45 milliamps. However, even 45 milliamps is not going to be enough, clearly, for 75 milliamps. So you're going to need to have 2 channels versus the 310, which, as I showed in the previous slide, is going to be able to easily drive 75 milliamps of current. And this is probably a very easy schematic to see a lot of the benefits from this, right? The 310 solution is much cheaper and it's smaller. Like, you're cutting the components and the size of the board basically in half. All right, now the final one, the reference buffer / shield amplifiers. This one is something a lot of people don't think about for something that most of us consider, okay, steady state voltage. It's kind of building a reference buffer, AKA a supply voltage. But there is still a transient, there's still transient signals that occur during startup or when there's a switch in voltage and current. This is this can be problems for amplifiers since usually reference buffers have large value capacitors, and anyone who's worked with amplifiers before knows that the larger value capacitor on the output can cause issues for op amps trying to drive it. It can cause stability issues, even during these startups for a reference buffer. So you can see on the right-hand side for the voltage versus time and current versus time, we're comparing the 2310 against the OPA 313. The OPA 2310 has a much smaller overshoot, as well as being able to settle down at like less than 100 microseconds, versus the OPA 313, which has enormous overshoots and a ringing that goes on to almost 500 microseconds. This is a result of the 2310s having a much higher output current drive. It's able to charge the capacitor up quicker and stabilize the output faster as a result of that, versus the 313, which is struggling and hitting its maximum current output. So if you want to have a faster settling time as well as less overshoot, then you're going to want to go with a higher output current device like the OPA 2310. I'll go a little briefly over the next few slides, but these are common electrical characteristics you can find in the data sheet, going over the output voltage swing and output current. So the tested swing with 50 milliamps, it's actually pretty unique to the 2310. Most devices don't test with 50 milliamps in a typical application spec, but we have this, we made sure to test all of our op amps and guarantee that this will be able to operate at 50 milliamps in a normal linear mode versus, versus most devices which they just mention having like a 10 kilo ohm load and they don't mention the output current. The next 2 parameters, they kind of give you a good idea of some of the short circuit current as well as voltage swing, but they don't really provide the full picture. I tend to look at, if you can change the next slide, the typical characteristic curves, or as we call them, claw curves, that really showcase what your expected output voltage swing should be at a specific output current. In this case, the graphs shown here are typical. I want to really emphasize that. When you're looking at these characteristic curves, they are typical curves. We always recommend giving yourself minus 20% for all your output load tolerances. So if you're saying, okay, it's going to be about 2.45 at 100 milliamps, worst case scenario for process variation, it can go down to 80 milliamps at that same output voltage. This is, we also provide it with 5.5 volts and 1.8 volts just to showcase that you are going to have a change in your output current when you have different supply voltages. But another impressive thing about this is the OP2310 still is driving quite a bit of current even at 1.8 volt supply. In the example we have here, 5 milliamps with only a 0.2 volts drop from the supply rails. Finally, let's talk about, until I turn it over to Bhuvan, I should say, but the two packages that we have for the 2310 that have power pads are the DSG package and RTE. We understand that some customers might be a little concerned with having such a small device that has like driving a bunch of output power or output current, and that's why we have these packages available so that they have a thermal pad to help cool the device down and prevent any heating. All right, I'll turn it over to you, Bhuvanesh.
So we talked about the high output current scenarios and applications. Now we'll talk about how to lower your power consumption with OPA310. So let's look at a typical amplifier signal chain. It's going to have a sensor, gain element, and a ADC. A sensor usually has a longer latency time and they are left always on. Whereas to reduce the power consumption of ADC, it is a popular method to actually use it in burst mode or duty cycle mode. Now, with respect to the gain element, you have two choices. You could either leave it always on like your sensor, or you can operate it in duty cycle mode like your ADC. So which option to choose actually depends on your application. So please note, right, when you go with the first option of keeping the amplifier always on, I have listed some low power amplifiers here which have hundreds of nanoamperes of quiescent current. These amplifiers have slightly lower bandwidth and a higher noise and a higher output impedance as well. If your application is actually going to be less than 100 hertz of bandwidth or so, you are possibly okay using a low bandwidth amplifier as long as your thermal noise floor numbers are acceptable for the SNR you're targeting. But if your signal bandwidth is higher than 10 kilohertz, and if you require a good signal to noise ratio, you are better off using an amplifier that can deliver that performance and then save power by duty cycling or turning on and off the amplifier as and when required. In the next slide, we will cover how OPA310 fares in this on-off scenario in comparison to few other TA amplifiers over a 1 millisecond time frame. So now, talking about duty cycling the amplifiers, we have different choices, right? I have listed 3 amplifiers with 3 different bandwidths along with OPA310. When you are duty cycling the amplifier, the most important thing you have to worry about is keeping the on time of the amplifier as low as possible. The on time of the amplifier is the summation of amplifier enabled time from shutdown and as well as the settling time for the ADC to take a proper sample. And if you kind of add the two of these times, that's the total on time. And as you can see, OPA310 achieves a very low total on time when compared to rest of the amplifiers with different bandwidths noted down here. And with the lower on time, you can achieve the lower duty cycle over the 1 millisecond time frame we talked about. Next, we want to worry about what is the power consumption over this on time and off times. We said with the lower duty cycle, the amplifier is going to be off for the majority of the time. So you possibly want to choose an amplifier that has the lowest quiescent current when it is in shutdown. As you can see, the OPA310, which is the single channel device, has just 265 nanoamperes of quiescent current in shutdown when compared to rest of the amplifiers that is shown here. What does this actually mean? Now you take the on current and the off current and average it over the on times as well as the off times over the 1 millisecond time frame. The OPA310 comes out to just consuming 0.69 microamps over that entire 1 millisecond time frame, which is low in comparison to all the other amplifiers according to their own enable settling times and quiescent currents in enable as well as shutdown modes. Also, now if you look at the thermal noise floor, OPA 310 achieves one of the best thermal noise floors when compared to rest of the thermal noise floors you have from the other amplifiers. So all in all, I want to say OPA 310 enables duty cycling to achieve a good power to performance balance, right? So this is all considering the static power consumption. There is also a dynamic power consumption portion of it. And as long as the dynamic power consumption, depending on your load, is comparable to your static current consumption, the calculations shown here and the performance shown here with OPA 310 is going to be better. And here are the electrical characteristic specifications of OPA 310 that I want to draw your attention to. Here is the 1 microsecond enable time and also the 265 nanoamperes of quiescent current in shutdown for the single channel. Now, if you go to dual and quad channel, the shutdown current for amplifier drops even lower. Lastly, in the typical characteristics curves, I want to mainly draw your attention to this. So this is where we are providing the enable signal, and you can see in the red color, the amplifier comes up, turns on, and it is settling to almost its final value all within 2 microseconds like we showed in the previous slide. So this is what would enable duty cycling very easily with OPA 310 when compared to the rest of the amplifiers out there. Lastly, the fail-safe EST. So this is the typical amplifier EST structure that is common with many of the amplifiers in the industry. You would have EST diodes from either of the inputs to the power supply. And these EST diodes can be problematic when your sensor is on and when the amplifier power supply is floating. What can cause this sensor on and the power supply floating scenarios? 2 things. It could happen during the amplifier power sequencing, or it could happen when you use separate power supply between amplifier and sensor to have a better sensor sensitivity in some cases. During these scenarios, let's say if your sensor is on and if your amplifier power supply is floating, in this case I've picked a sensor voltage of 3 volts, that could possibly turn on this EST diode and put about 2.3 volts on the amplifier power supply. This power supply of 2.3 volts is enough to turn on the amplifier, causing a quiescent current of 165 microamperes to be consumed through the sensor, thereby heavily loading the sensor. And more than that, it could also create a possible fault voltage at the output, depending on what you have on the feedback network. So this is a problem that most of the amplifiers have. You know, the back powering, as we call, which is powering the amplifier through the sensor, causing sensor loading and false signal at the output. In OPA 310, we have completely solved this problem. We have gotten rid of this EST diodes to positive rail, and we have achieved the EST performance with a different EST structure. Since there is no diodes to positive rail, even when the sensor is on, when the amplifier power supply is floating, this parasitic path is broken down. And with this parasitic path broken down, you maintain a high input impedance for sensor all the way from negative rail up to 6 volts from the negative rail as far as the sensor output is concerned. And also it maintains a high Z for the amplifier output downstream into the ADC, preventing any faults. So along with all of this EST improvements, we still achieve 8 kV of HBM EST performance with OPA 310, and most amplifiers out there are typically hovering around 2 kV or 4 kV EST performance. Lastly, with this fail-safe EST and very good enable and shutdown quiescent current performance characteristics, we are still offering OPA 310 in some of the smaller packages out there. In the 4-channel, we are offering it in a 3x3 RTE, and for a 2-channel, we are offering it in 2x1.5 RUT package. This enables you to use OPA 310 in small size battery powered applications, really taking advantage of the quiescent current consumption in enable mode and disable modes. this is how you can finally get started with OPA 310. We have links to the product folder, the sample pages right here. And along with that, we have a lot of technical content that we are going to deliver. We have already published the ESP, op-amp ESP protection structures, which talks about the fail-safe ESP and the Howland current pump. And we have a couple of content plans to talk about the fast enable, as well as the benefits of high output current. We have the SPICE models that you can use to simulate and start your reference design. And finally, we also have the surface adapter EVMs and the small dip EVMs to get started with the evaluation. I'll quickly touch on the surface mount adapter EVM. This is basically a board which is developed by our applications engineer, Robert here. It enables you to actually use a smaller package on a bigger layout pattern that you have on your board to evaluate the packages when you have different, when you are trying to move from a larger package to a smaller package, right?
Yeah, and I also just want to add, this allows, let's say we're out of one of the devices on TI.com, we're out of stock on an SOIC package, a dual SOIC, but we have a DDF package in there or another alternative package. The customer saying, well, you don't have the package, I can't evaluate your part in my board. Now you can with the adapter board. Like you can put this directly on a customer footprint with our smaller package, and the customer can start evaluating it in their system, which is a super powerful and helpful tool to get designed in. Anything to add to that, Bhuvanesh?
Yeah. So yeah, this is already released, and a lot of people out there are already trying it out. So definitely helps you evaluate multiple packages on your existing footprint without going in and modifying your board, right? So I think this is a good one. That kind of covers up our presentation for today, and thanks a lot.
All right, thank you. And thank you everyone for attending today's MPU webinar. The recording and PDF version of the slides will be available at ti.com/MPU. See you next week for our next topic, introducing the new ARM Cortex MO plus MCU portfolio. Thank you everyone and have a great day.